Hi, my name's Andre He. I'm a quantum hardware engineer here at IBM Quantum, and today I'll be talking about quantum benchmarking and how we benchmark our quantum computers here at IBM Quantum. So first, a brief outline of what I'm going to be talking about today. I'll start with some background about qubits, quantum gates, and quantum noise, and then move on to exactly how we benchmark our IBM Quantum Systems. I'll talk about our device level benchmarks, where we measure device level properties. And then I'll move on to subsystem level benchmarks, which have more to do with the gates that we've calibrated on our quantum devices. And the rest of this topic will continue in part 2 of this talk, which will actually be given by my colleague in part 2. So I wanted to start out by first going over our development roadmap for IBM Quantum that we've used to overview. So first, I wanted to take a step back and look at our development roadmap here for IBM Quantum, where at first in 2016, we put our 5-qubit devices on the cloud up until today, where we have Eagle and Heron systems available to our clients, which have 127 and 156 qubits. And all this time, as we've been releasing higher scale, higher quality, and higher performance devices, we've also developed benchmarks all the way from granular benchmarks that measure device quality all the way to holistic benchmarks, which measure the overall performance of our devices, including both the classical and quantum stack, all the while. So first, I wanted to go over some background information that'll help us when we're taking a deep dive into these benchmarks. So qubits, as we all know, their state can be described by a wave function, which is a superposition of the 0 and 1 computational basis states. And each of these basis states has associated with it an amplitude that can be a complex number. And a convenient way of representing this state is the block sphere representation, where each state is represented by a vector on this block sphere below, which has an angle from each plane associated with it. And quantum gates act on these quantum states and are unitary operations that rotate the state vector around the block sphere. For example, here we have examples of quantum gates that are rotating these state vectors around different axes in the block sphere. An important thing to note is that ideal gates preserve the length of this state vector and also rotate it by a precise amount. And now, having just gone over the ideal case for these unitary transformations, I've included here some cartoons of what can happen when non-idealities occur, which we call quantum noise. For example, miscalibration can cause the axis of rotation of a pulse to become miscalibrated and the action of a pulse to, as a result, become inaccurate. State preparation errors, where if we intend to initialize a qubit in the 0 state but fail to do so, or vice versa for the 1 state, can cause the states accessible by the system to become slightly deformed. And also, dephasing noise and amplitude damping noise can also cause deformation of these accessible states on the block sphere. In addition to that, leakage is also an error mode whereby the qubit state escapes from the computational manifold and can cause all sorts of errors. And in addition to that, crosstalk can also be an issue where we have correlated errors between multiple qubits. So in a more formal sense, all of these quantum operations are described by completely positive trace-preserving or CPTP maps, and these can be represented using operator sum representation. So quantum operations are described by completely positive trace-preserving or CPTP maps, and these can be represented using operator sum representation. For example, here we have a quantum operation which acts on the density matrix of our system, along with the completeness relation on the side. In the ideal case, with an ideal unitary transformation, this quantum operation would be represented simply by only a unitary matrix sandwiching this density matrix. But in the realistic or non-ideal case, noise can cause this rotation to deviate from the ideal rotation, involving over or under rotations and changes in the magnitude of the vector, like I described before. Some examples of these noise modes are bit flips, phase flips, and bit phase flips, which are represented respectively by the poly x, z, and y errors. These flips reflect the block vector that we mentioned before across the x, z, or y-axis planes. And an example where these three work together is depolarizing noise, which replaces the quantum state with a maximally mixed state with some probability p. So in this expression below, we have that the original density matrix transforms with probability 1 minus p to the original density matrix, or with some probability p over 3 to the same density matrix sandwiched by bit flips, phase flips, or bit phase flips. So in this case, what one can intuitively understand this is that the quantum state has some probability of no error occurring where it stays in its original state, or some probability where it's equally likely to be acted upon by bit flip noise, phase flip noise, or bit phase flip noise. And the way that one can intuitively understand this visually is that it shrinks the block vector towards the origin uniformly. In addition to these bit flips and phase flips, we also have amplitude damping noise, which models energy relaxation, for example, spontaneous emission in our system, which can cause transitions from the excited state to the ground state. And this can be visualized as a block vector decaying towards the south pole of the sphere. In addition to that, there is also phase damping noise, which is similar but not quite the same, which models the loss of quantum coherence without the energy loss, as we have in amplitude damping noise, and it's more of a purely quantum form of noise. This shrinks the transverse components of the block vector towards the z-axis, and eventually it will cause the quantum state to decay towards a fully mixed state, which we see as a classical mixture of the 0 and 1 state. So here I've summarized in this table some forms of quantum noise, some of which I've talked about and some of which are beyond the scope of this talk, but I've summarized here just to be complete. So we've talked about decoherence, gate miscalibration, and we'll also talk about state preparation and measurement errors. And some other forms of noise that we won't really get into in this talk, but are also important to know, are crosstalk and leakage and non-Markovianity, which can affect our quantum results. So why is characterizing noise important? So first off, noise limits the performance of our quantum algorithms. Secondly, noise is hardware specific and needs to be empirically characterized. And another important thing to note is that noise also changes over time. So it's important to continually benchmark our quantum devices to track how the noise that each device's experiences is changing over time. Additionally, accurate noise models enable error mitigation on near-term devices, for example, zero noise extrapolation or other methods like probabilistic error cancellation, simulation of realistic devices for algorithm validation, for example, if someone wants to test their quantum algorithm or validate that it just works before running on a real quantum device. And lastly, accurate noise models are also important for qubit layout selection, which is really important for our near-term quantum algorithms because we want to choose the best possible qubits to execute our algorithms on. Now, I wanted to also touch on benchmarking IBM Quantum Systems and how we can take a look at these benchmarks on the cloud. So here on the right, I've pulled up the device card for IBM Fez, which shows a lot of our device parameters that are available. For example, here you have the number of qubits, but we also have two qubit errors using different methods. We also have some higher order benchmarks like a layered 2-qubit error and CLOPS, which my colleague Majo will be talking about in part 2 of this series. And we also have median 2-qubit gate errors, which for the Heron architecture is the controlled C gate, median single-qubit gate errors, median readout errors, and median T1s and T2s. And on the left here, we have the device map, which shows us in a heat map format how these devices' errors look like physically. So we can see in the drop-down menus that we can select T1s, T2s, readout errors, and also 2-qubit gate errors here to see exactly how things look like on a qubit-by-qubit layout. So now let's move into a deep dive on exactly how we measure these benchmarks, the circuits, and the circuits that we run. So I'll be So we like to classify these benchmarks into a hierarchy. And at the very bottom of this is what we call device level benchmarks. And these device level benchmarks measure properties of the device. So for example, T1, T2, a quantum and classical crosstalk, connectivity, coupling rates, readout rates, and other properties of the device that are mostly determined by the qubit architecture, the device design, the fabrication process, and also the electronics that we use to control these devices. And moving up, we have subsystem level benchmarks, which after we've calibrated our qubit control, we're able to measure. These are, for example, single and 2 qubit randomized benchmarking, qubit readout, assignment matrices for qubit readout, and other benchmarks that are associated with circuit compilation and the classical control that we have for our quantum computers. And at the very top, we have holistic benchmarks. And holistic benchmarks really give us an idea of how our quantum computers perform with large workloads and utility scale workloads. So for example, these include things like quantum volume, CLOPS, and layer fidelity. And these, my colleague Majo will be getting to in part 2 of this talk. So let's start out with device level benchmarks. So the first one I want to talk about is T1, in which we're measuring the energy relaxation time of a qubit. So the goal here is to measure how quickly an excited qubit in the 1 state relaxes to the ground state. And the circuit here is quite simple. We prepare the qubit in the excited state using an X gate or a pi pulse. We wait for some amount of time t, and then we measure back in the computational basis. So the protocol here is that we prepare the qubit in an excited state using the X gate. We wait for a delay time t, and then we measure in the computational basis. We repeat this for multiple delay times t and collect the probabilities at each time step. The probability of measuring in the 1 state at each time step, P1. And as we can see here, for each of these delays, we have a characteristic P1, which is measured by performing this circuit many, many times in order to collect statistics. And at the end of the day, when we've collected all of these P1s for all of these delay times, we fit an exponential model to it. And we fit multiple parameters. We fit an amplitude, a base of decay, but the important parameter that we're looking for here is the decay constant T1, which gives us an idea of how quickly this qubit relaxes to the ground state. And here I've taken some data from qubit 104 on one of our herons, IBM Marrakesh, to illustrate what these T1 curves look like. And next, let's move on to T2, or the dephasing time. So the goal here is to measure how quickly phase coherence decays. And there are multiple different ways to measure T2 on our quantum devices. We use a variation of T2 called the Han-echo experiment, where we do repetitions of an echo sequence in order to filter out some lower frequency noise that might affect our results. So the protocol here is to first prepare the qubit by applying a pi over 2 gate that puts the block vector of the qubit on the xy plane. We repeat the echo sequence, which is here. It consists of a delay, a pi pulse, and a delay. We repeat that n times. Now here it's only repeated once, but essentially if one repeats this echo sequence more times, one can get better filtering of this noise that we're trying to filter out. And then at the end of the circuit, we apply a pi over 2 gate to bring the qubit back to the computational basis, and then we measure. And as we did with the T1 experiment, we measure with multiple delay times, and we collect probabilities P0 of t. And the model that we fit is very similar to the one that we do for T1, where we have an amplitude term, a base term, and also a decay term, where we're trying to back out T2 from that delay term. And after fitting this, we have here on also a qubit from IBM Marrakesh, a T2 experiment that was run. One important thing to note is that even though this decay does qualitatively look similar to T1, it is different because as I mentioned in a previous slide, for T2, the qubit eventually dephases to the maximally mixed state. And in the maximally mixed state, we'll be measuring an equal superposition, essentially, of the 0 and 1. So we will be decaying down to a base population of 0.5 here. And moving on, the next type of error that we classify on our devices are readout errors. The goal here is to estimate the probability of misidentifying a measurement outcome of a known state. So for example, if I prepare a 0, I want to know how many times will I measure a 0 and how many times will I erroneously measure a 1, and vice versa for the 1 state. The protocol here is fairly simple. So first, we prepare the qubits in all possible bit string combinations, and then we measure in the computational basis. And then we repeat this experiment for statistics. And from these measurements, we're able to build error models. So here we have the assignment matrix, where on the diagonals, we have the measurement fidelities for each state that we've prepared. And on the off diagonals, we have the errors, where we prepare one state but measure the other. And here on the right, I have a sample circuit diagram of one of these circuits where we prepare the all 0 state and then measure, and then on the bottom, prepare the 1 state and then measure. And in principle, these are only 2 of the circuits. You could also measure all possible bit strings, but we see that this quickly blows up because even for 4 qubits, we have 16 possible states. So it grows exponentially with the number of states that we have to measure grows exponentially with the number of qubits that we have. So after talking about readout errors, let's move on to what we can use these readout errors that we measured for. So readout error mitigation is a common strategy that we use in order to counteract the effect of readout errors. So 2 of the most common methods are matrix inversion. So the main idea behind matrix inversion is that we assume that the noisy measurement results are the result of the true measurement results multiplied by some noise matrix that we've measured. Then, if we just invert this equation, we can estimate the true measurement values by multiplying the inverted error matrix by the noisy measurement values. But you can see how this doesn't scale that favorably. As I mentioned in the previous slide, we have to measure over all possible values, all possible bit string values for this n-qubit system, and that scales exponentially. So while this might work for a handful of qubits, very quickly when we get to many qubits, this method stops being tractable. One method that improves on this a little bit is called quasi-probability inversion, where mitigation is usually performed locally per qubit, and then an overall mitigation matrix is constructed using tensor products of these smaller local, so 1 or 2 qubit confusion matrices. And these local noise assumptions allow us to build a scalable estimator because we don't have to measure across all of these possible bit strings. Then each measurement outcome is sampled with weights that may be negative or greater than 1. This is why it's called quasi-probability inversion, but these average to the correct result when we're talking about observables. And over here, I've included some examples of the results that one might see when applying quasi-probability inversion both to counts and also to the expectation value of our observables. So after talking about these device-level benchmarks, which have to do mostly with device properties, let's move on to subsystem-level benchmarks. So subsystem-level benchmarks usually have to do with qubit controls after we've calibrated them, and really what we want to see is how well are our gates performing. So one of the most basic ways to do this is quantum state tomography. This is a technique that's been around for a while, and the goal is to reconstruct the density matrix of a quantum state by preparing the state many times and then measuring them in a complete basis. So the protocol is simple from what I've just described. So first, prepare the qubit in the state of interest that you want to measure, and then measure the state using a complete set of basis states. One can see that this is also a relatively expensive operation because the number of basis states grows exponentially as the number of qubits as well. Here on the right, I've shown some results from a quantum state tomography experiment using Qiskit, and we can show that we're measuring the density matrix elements here on the right. And on the top here, this is just a simple cartoon sketch of the circuit diagram for a quantum state tomography experiment. And an extension of this is quantum process tomography, where the goal is to reconstruct a quantum operation from its effect on a complete set of inputs. So not only do we want to see the effect of this process on a single input state, but across all possible input states to reconstruct how this process acts. So the method here is to prepare a complete set of input states, apply the process circuit for the process that you're interested in, and this can be pretty arbitrary and, for example, could be a block for an algorithm or even a complete circuit for some sort of quantum algorithm that one would want to run. And then at the end, perform quantum state tomography on the output. And from this, because we are starting from a complete set of inputs and also measuring in a complete basis state for the outputs, we can reconstruct this process. This also has some of the same. Even though we're able to rebuild this process in great detail, this has some of the shortcomings that we've also seen with quantum state tomography, in that the number of circuits and the number of measurements that we need to perform grows exponentially with the size of the system that we're wanting to measure. So seeing that quantum state tomography and quantum process tomography, although they can give a very detailed picture of what exactly is happening in our quantum system and exactly how noise is affecting it, we can see that once we want to move to a larger number of qubits, that these methods can be very inefficient. So next, we'll talk about some methods that are really representative of a class of methods that utilize some convenient properties of randomization in order to obtain average gate fidelities quite efficiently. So let's move on to randomized benchmarking. The goal here is to quantify the average error rate of quantum gates. And the protocol is to first generate a sequence of random Clifford gates. And a convenient property of a Clifford gate set is that they are efficient to compute classically. So we can for any sequence of random Clifford gates, we can efficiently compute a gate that will actually invert that whole string of Clifford gates and append that gate to the end of the circuit, which returns this qubit to the zero state, and then measure. So for this circuit here, for example, on the right, we would be starting in the zero state, appending our random Clifford gates, and then at the end appending an inversion gate that we've computed. So ideally, when we get to the end of this circuit, we will want to measure a zero. But because of the presence of noise, we won't measure a pure zero state population all the time. And what we do is we repeat this process for multiple sequence lengths and then average over many random sequences. And the error model that we fit to this decay will be exponential in nature, and from the base of the exponential, we're able to extract an average error rate, which characterizes the fidelity of our gate. And for example, here on Marrakesh, on qubit 124, I've included the results of a single qubit randomized benchmarking experiment, where we're tracking how the population of the zero state decays with respect to the Clifford length, and we find that we're able to extract the average gate fidelity from here. And moving on, let's see if we can extend this to 2 qubits, since we've just looked at the single qubit case. And it's very simple to do so. It's an identical process to the 1 qubit experiment, except now we use a 2 qubit Clifford group. An additional consideration here is that since we're using the 2 qubit Clifford group, and the 2 qubit Clifford group includes both single qubit and 2 qubit gates, the error per Clifford value obtained by the experiments indicates a depolarization which is a composition of both the single and 2 qubit errors. So if we're in a regime where the 2 qubit gate errors are much, much more dominant than the single qubit gate errors, then this isn't much of an issue. But one needs to be careful about exactly which errors we're characterizing when we get to a regime where 2 qubit gate errors and single qubit gate errors are more similar. Even though that we've gained a lot just by using the properties of the Clifford group and also randomization for randomized benchmarking, and also in principle, randomized benchmarking scales to arbitrary n-qubit gate sets, there is still a bit of a price to pay here because the size of the Clifford group quickly scales with the number of qubits. So if we want to extend randomized benchmarking to arbitrary n-qubit gate sets, it can be quite expensive after we get past Clifford groups that include more than a few qubits. And now that we're done talking about 2-qubit randomized benchmarking, I wanted to provide some resources where you could learn a little bit more about these different flavors of randomized benchmarking that have been developed over the past few years, which improve randomized benchmarking for specific use cases or optimize its performance. And there's quite a bit that has been written in the literature on randomized benchmarking, and it would be many more talks in order to go over all of them in detail. So I'll just leave this here for people to go over in their free time. And just on a final note, all of these experiments that I've shown today are part of the Qiskit experiments library. And I've included some links here that you can feel free to visit on your own time to look at these experiment manuals, which are in the form of Python code that you can run in a Jupyter notebook on your own computer and submit jobs to actually benchmark for yourselves the performance of our quantum devices. And these include experiments all the way from T1 to these randomized benchmarking experiments that I've just talked about. And these are also the experiments that we use ourselves here at IBM Quantum to benchmark our own devices and provide their performance to you on the IBM Cloud website. So with that, thank you, and I hope you stay tuned for the second part of this talk with my colleague Majo.
Hi, my name is Majo Lozano, and I'm a quantum hardware engineer at IBM Quantum. Today, I'll be talking about quantum computing benchmarking, and this presentation is the second and last part of a benchmarking series, and it is also part of the Qiskit 2025 Summer School. So, if you're watching this, you might have also watched the first part of the series with Andre He, one of my coworkers, where he talked about device metrics and subsystem benchmarks. You can see some of these examples in this pyramid, starting with individual qubit metrics at the very bottom, like relaxation time T1 and the coherence time T2, and also single qubit and 2-qubit control benchmarks, like single qubit randomized benchmarking, 2-qubit randomized benchmarking, and readout fidelity. All qubit control operations have both a fidelity and a runtime associated with them. And while it is incredibly useful and necessary to benchmark these operations in an isolated manner, that is, at the single and 2-qubit levels, we should not forget that if we want to run quantum circuits at the utility scale, then we also need to benchmark the state of a system as a whole. And this is what we will be talking about today, something that we call holistic benchmarking. But before jumping into holistic benchmarks, let us briefly introduce one more 2-qubit level benchmark, which gives us a better idea of the performance of entangling gates in a system. And this is called the Hellinger fidelity of a Bell state. This test helps us benchmark entangling 2-qubit gates, in this case the CNOT gate, which you can see here, and it basically measures how well a generated Bell test matches an ideal Bell state. For reference, a Bell state is a quantum state of 2 qubits that is maximally entangled. There are 4 of these states, and they can all be generated by applying a combination of the Hadamard gate, an X gate, and a CNOT gate. The 4 Bell states can be seen below. In this step, we generate the following Bell state by applying a knot number of CNOT gates. The circuit can be seen here. We then estimate the Hellinger fidelity, which quantifies the overlap between the measured and ideal distributions of measurement outcomes. This gives us a better idea of the performance of the CNOT gate. The Hellinger fidelity is given by the following formula, where h is the Hellinger distance. It is the distance between 2 count distributions. This test is sensitive to qubit initialization, single qubit and 2-qubit errors, and readout errors. So, with this, we finalize the single and 2-qubit level benchmarks, and we can now turn to device-wide benchmarks, which are the holistic benchmarks like quantum volume, layer fidelity, CLOPS, and mirror circuit. Let us start by introducing mirror circuit, which is a primitive quality benchmark. It's a straightforward way to test how accurate are the expectation values, or observables, from a utility scale circuit. We define such a circuit to include roughly 5,000 gates. The main idea behind the mirror circuit benchmark is to run a circuit followed by its inverse, and to compare the observables to the ideal values. This is a useful way to test error mitigation techniques, for example, as it offers straightforward ways to compare experiment results. The plot we see on the right, in this case, compares the accuracy of observables between raw experiments and experiments that apply error mitigation techniques. We see this for two Heron devices, Torino and FES. This plot offers an easy way to see that the observables produced with error mitigation techniques are more accurate to the ideal values than the ones produced without it. So in this particular case, more than 40% of observables are within a 10% range from the ideal outcomes. The choice of the mirror circuit is, in this very case, characterize time. That is, the evolution of a one-dimensional Ising chain, followed by its inverse, as one can see here on the right. This action is essentially equivalent to applying the identity, and this makes it easy to estimate how accurate are the observables. On the plot here, we see the distribution of the difference of observables minus the exact case, and we care about observables within a 10% distance from the ideal solution. In this very case, which is one of our most recent Heron R2 data, we see that roughly 85% or more of our observables are within this range, which is pretty good. And now we can move to one of our main benchmarks that we'll be introducing today. This one is called a quantum volume, and it indicates how faithfully a square quantum circuit of depth d can be implemented. We'll discuss briefly what we mean by a square quantum circuit. Quantum volume is what we would call a pass or fail test, and it was designed to be independent of the quantum computer architecture. This allows for different types of architectures to be compared to one another. Quantum volume is encapsulated by a single number, and it captures the performance of the best subset of connected qubits on a device. It is given by 2 to the d power, where d is the size of the subset of qubits used, as well as the maximum depth of the circuit run. Hence, our definition for square circuit. We should also note that quantum volume is sensitive to coherence, gate fidelity, crosstalk, and measurement fidelity. It is also influenced by connectivity and compilers. IBM last reported achieving a quantum volume of 512 back in 2022. This is equivalent to 2 to the 9th power. On a device called Prague, which you can see here, a Falcon processor with 27 qubits. But it hasn't been the only company to report such metrics. Trapped ion architectures, for example, have been doing well in this metric too. Quantum volume is a holistic metric because it cannot be improved by just improving one aspect of the system, but rather requires all parts of the system to be improved in a synergistic manner. So, this is what running the quantum volume benchmark looks like. We first define a quantum volume circuit that is d layers deep. A layer is composed of random permutations of single qubit labels, which is the pi layer here, followed by the application of arbitrary 2-qubit gates, which is the SU layer here. After we define the circuit, we simulate the ideal results classically, so we have a baseline to compare the experimental results against. We care about the heavy output states, which are the states that are most likely to occur. The heavy output states are defined by having a probability of occurring higher than the median of the set of output probabilities. We then run the quantum volume circuit on the quantum computer and obtain the heavy output states from the experimental results. This will allow us to compare them with ideal ones. If more than 2/3 of the ideal heavy outputs were generated, we say that the device passed the test. In such case, we increase the number of qubits and layers by 1, so the new depth is d plus 1. We generate a new circuit of such depth, and then we run the test again. If, on the other hand, less than 2/3 of the heavy output states were generated, then we say that the device failed the test. Finally, we define quantum volume to be 2 to the power of d, where d is the maximal square circuit size that successfully generated more than 2/3 of the ideal heavy output states on the device. Quantum volume is a great benchmark and is widely used in the industry, but there are some points that we should take into account. First, quantum volume is a discrete pass or fail test, and it relies on classical simulation. It is limited to scales that are tractable. For large enough systems, quantum volume experiments will soon become too large for us to simulate classically, so we won't know whether or not our systems can pass the test. Second, it does not provide individual gate information. As a discrete benchmark, quantum volume does not indicate continuous changes in gate improvement. And third, this benchmark reports on the performance of the best subset of qubits on a device. That is, it is a high flyer benchmark. For devices with more qubits than log to the second power of quantum volume is not the best representative of overall quality. Quantum volume was designed to run on an all-to-all connected system, where every qubit can talk to every other qubit. In our 2D topology, this means that every step up in quantum volume is taxing on the fidelity and the number of gates, since we need to introduce many swap gates to move information around. As a reminder, each swap requires 3 CNOT entangling gates. Looking into the future, we need an additional metric that tracks continual improvements on devices with more than 100 qubits, and that helps us understand the system's ability to run large-scale error mitigation algorithms. Ultimately, quantum volume is still a very strong test of systems performance, which we will continue to track. But as we are continuously improving scale and quality, we need to augment our characterization portfolio with a new metric to benchmark against. In this is where layer fidelity steps in. Layer fidelity provides a benchmark that encapsulates the entire processor's ability to run circuits while revealing information about individual qubits, gates, and crosstalk. This benchmark captures the performance of a set of n fully connected qubits over m layers, and is insensitive to state preparation and measurement errors. The choice of n is flexible, but we usually select a set of n qubits that is comparable to the size of a device. This allows us to capture a device overall performance. In this case here, we're selecting the red chain on the device. And this is how layer fidelity is usually run. So once we have our fully connected set of qubits, we partition it into m layers. For a one-dimensional line of qubits, like the one that was red we saw on the other slide, the most efficient value of m is 2. But one can select different values to generalize it to all connectivities. The objective here is to split this set of qubits into different layers such that each qubit in a layer has at most one 2-qubit gate acting on it. And we call these disjoint layers, like we can see here. Now, on each disjoint layer, we then run the following circuit, which is a mixture of simultaneous direct randomized benchmarking with timing barriers and twirling through random 1-qubit cliff roots. Because the protocol performs randomized benchmarking simultaneously, layer fidelity is able to capture crosstalk. As a reminder, randomized benchmarking applies a set of randomized Clifford gates and then runs an operation that we know mathematically is the inverse of such operation. If any of the qubits do not return to their original state upon measurement, then we know there was an error. We can extract gate fidelities by repeating this process multiple times and fitting the data to an exponentially decaying model. Once we get the individual process fidelities, we multiply them to get the fidelity of the current layer. And finally, we multiply the fidelity from each layer into a final number, the layer fidelity, which we can see here. We also define a size-independent quantity, which we call error per layered gate, or EPLG for short, given by this formula here. And as the name suggests, it is the average error for each gate in these layered circuits. Here's a graph showing a comparison of the distributions of 2-qubit errors from layer fidelity and isolated benchmarking from randomized benchmarking. As we were mentioning before, layer fidelity is based on the idea of simultaneous randomized benchmarking and is thus capable of capturing crosstalk, which the ideal isolated case does not. We can compare the distribution for 2 of our processor types, Heron and Eagle. Heron is our highest performing processor to date, and one can see from the 2-qubit error distributions on the plot, which are the red distributions here, that the 2-qubit errors are quite similar for layer fidelity and isolated randomized benchmarking, which shows that this processor can eliminate most crosstalk. All in all, layer fidelity is an extremely valuable benchmark and a great complement to quantum volume. It captures device-wide performance with a single size-independent quality, which we called error per layer gate, or EPLG for short. Layer fidelity also reveals information about individual qubit, gates, and crosstalk. And it can report on the performance of an entire device, rather than reporting on a smaller subset of high-performing qubits. The results of layer fidelity can be directly looked up on the IBM Cloud platform. Users will find the independent size quantity error per layer gate right here, next to the best 2-qubit error. Our highest performing devices exhibit numbers as low as 4 to the negative 3, which translates to 4 to the negative 3 2-qubit errors per layer. Okay, so far we have discussed holistic benchmarks based on quality and scale, but let's not forget that speed is also an important factor in evaluating the performance of a device. And this brings us to the last benchmark we'll touch on today, CLOPS. CLOPS stands for circuit layer operations per second, and it measures how many layers can be executed per unit of time. We'll borrow the concept of a layer that was introduced in the layer fidelity benchmark. This allows us to mimic real-world scenarios. CLOPS takes into account the following parts for calculating the total time. The first and most straightforward part is the time it takes to run the circuit on a device. We call this the circuit execution time. Second, because we always collect multiple shots in an experiment, we have to factor in the delay time between circuits. And lastly, we need to factor in the runtime compilation and data transfer time. This is the time it takes to prepare the circuits, that is, updating parameters and generating the waveforms, and the time it takes to transfer information, such as submitting the circuit to the backend, initializing the instruments, and getting the experiment results back. Here are some more specifics to CLOPS. Because the goal is to show that the software and hardware can execute utility-scale circuits efficiently, CLOPS measures multiple instances of parameterized layers, as can be seen on the figure here. CLOPS can be measured on any circuit size of any width and number of layers, but the default value we use is 100 by 100, since we believe this is relevant to utility-scale applications. So these layers here consists of 2-qubit gates that are fully executed on parallel across as many qubits as possible, as is the case with layer fidelity, and fully single-qubit rotations on all qubits. Then after we run this, we basically define CLOPS as a number of layers executed per second. The results of the CLOPS benchmark can also be found on the IBM Cloud platform, as is the case with many of the other benchmarks that we've mentioned today. Our Heron processors exhibit numbers as high as 210,000 circuit layer operations per second, as is the case with IBM Torino, and FES, which is another of our Heron processors, exhibits numbers as high as 195,000. Lastly, people can consult the open source repo, Qiskit device benchmarking, for learning more about these benchmarks and running them themselves. These span from layer fidelity, CLOPS, mirror circuit, and quantum volume to Bell state tomography. Thank you so much for listening to this presentation, and feel free to consult like any of the other IBM Qiskit resources for more.